1989.
Okay.
I think we're
So
live.
suspicious.
No, I
Are
just
we
wasn't
still?
sure. I wasn't sure if you were on 90 or not.
All right, we're live, but let's give it a few seconds so it's easier to edit. All right.
Okay.
Oh, I'm not orange anymore. Nice.
All right. Hello, everyone. Welcome to another episode of Quirkcast. This is your host Tim.
And I'm Mikey.
And this is Sahil. Welcome, everybody, to a brand new episode of Quirkcast. So before we get started, some logistical things. If you have any comments or questions, please do post them on the YouTube channel. And that way you can get to them during the episode. And so, yeah. So let's get started. So Tim, I was struggling to break apart an electron. Decided like, why not go for the next best thing, like a proton? So can I do it, or is my efforts futile?
It's
What do you
easier.
say?
Well, actually, the other day we were thinking about this question, and I did a little Google search. As we all know, Google is the source of all truth. It turns
Yeah.
out that if you put it in Google and ask, can we split a proton? It says no. The answer is no. You cannot
Really?
split a proton.
What?
So, okay, but let's give that perspective a go first. So, what do people mean when they say splitting a proton? I think a lot of people are referring to nuclear physics. So it's like if you don't know about the periodic table, there's there's hydrogen, helium, lithium, blah blah blah, all that, and all the different atoms are made of the nucleus of these atoms are made of protons and neutrons, and people have built accelerators to bombard them apart, to basically perform alchemy to turn one element to another, and it turns out that you could, break apart the nucleus into protons and neutrons. But from that perspective, it seems like the protons is the unit that becomes indestructible. So from that regard, it seems like the proton, you can't split the proton. But is that really the reality?
Huh.
Just so you know, that answer on Google, I believe it's from Reddit.
Is that right? Oh, well.
I mean, it's a very strong stance, right? We could debate, we will on the show debate whether or not it's possible to split a proton. So for them to just say, no, that's
Huh.
so upvoted a lot.
So apparently some person on Reddit saying you can't do it. Do you agree with that, Mikey, or is that guy right? What's going on?
I think their explanation for why it's not, it's fine.
But let's give them the particle physics perspective.
So what is the particle physics perspective?
It's a little more muddled. I don't know. I mean, so Tim, you're gonna say we cannot?
Well, I don't know. I think that there are multiple perspectives. I think on the one hand, there's some ways you can talk about it in which we cannot. But there's some other ways you can talk about it, and then we can answer. The answer will be yes. But each way of thinking about it actually brings out some new physics. So I think we should talk about both.
I think if you can split an atom, you can split a proton.
What makes you so confident about that, Mikey?
I mean, it depends on what you mean by split, right? So we say split an atom, we mean, can we, well, first of all, we typically imagine the atom being made up of smaller, more fundamental constituents. And when we say split, we usually mean being able to separate them. But for how long do we need to separate these things in order for we to say we split them? If I separate a nucleus from the electron of an atom for like 10 seconds, would you say that I've split it? What if it recombines after 10 seconds? Split it?
Yeah. Yeah, I'm gonna say yes.
So, how long can you pull a quark out of a proton? The time is not zero. It's actually a very short amount of time that a quark can exist outside of what I would call the proton. But
So wait, let's take a step back for a moment. You mentioned a new term, quark. What is it?
Oh,
Like what does that have to do with the proton? Why did we talk about quarks now?
Yeah.
so yeah, I guess this goes back to so most people when they think of an atom and they think of splitting an atom, or I guess even more fundamentally when we think of splitting a tomato, let's say we think of a tomato being made up of like atoms, and you can split
Yep.
this set of atoms so it's in a different place from this set of atoms. If we think of tomatoes, not atoms. We can think of the same thing with atoms though. We can split the different constituent parts so that they're far apart from each other, and we would call it split. In a sense, protons can be thought of as being made up of smaller, more fundamental constituents, which we call quarks. For reasons we'll get into, it's a little bit harder to think of them as building blocks. I think they're building blocks.
Yeah. Well, yeah. Let's clarify a little bit. When we say quarks, I think the spelling matters. It's the Quark. Like maybe one day we'll finally go over the origin of Quirkcast, which is spelled with Quirk, right?
Yeah.
But what we're talking about is the Quark, the quark. So the proton turns out it's what we call a composite particle, that it is made of quarks and gluons. So normally
what we call
what we call quarks and gluons. And normally when we split something, like splitting an electron from the proton, it's like you take it away, and there's a sense in which they're completely separated. Like you can ionize an atom, right? But to some extent, they're still interacting, like gravitationally, minimally. So even this total splitting, it's not absolute, but it's pretty clean. It's a very clean way of splitting. But for the proton, it's a bit subtle, because even though a proton is made of quarks and gluons, if you try to pull one out, you kind of don't really succeed. That's why there's some physics in it that makes it such that it's not possible to actually just grab a quark or gluon out of a proton and to take a look.
You just have to do it really fast.
Yeah, so it turns out that the amount of time it takes, or the time scale at which things happen, is very important. It changes your perspective, basically, on what the image, what the processes look like. So.
Yeah. So I want to also kind of like take a step back. So you're saying that there are these, like, I'm using in quotes, like constituents or like basic building blocks, again in quotes, of a proton, which are these quarks and gluons. And what you're saying is it's difficult to grab an individual quark or gluon out of a proton due to reasons that we'll discuss in a little bit. But it's just hard to split it in that sense, because you can't really, like, might be like a strong interaction between the quarks, or how should I think about this?
There are rubber bands tying the quarks together.
Yeah.
So the harder you pull, the harder it pulls back.
How does that work? That's so. I mean, how's that different than like electrical attraction between like a positive and negative charge? That the more you pull, like it goes down, right?
Yeah. Most forces get weaker as they get farther away.
Yeah.
And that's why it's usually possible that you can split a planet from a star that's orbiting. Mm-hmm. You can split an electron from a nucleus that's orbiting. But physically it's hard to separate a quark from a proton because it's like an opposite force.
Yeah, this is what we call the strong force. It turns out that the strong force is it's got very different characteristics. So that's why you can cleanly separate out an electron from a proton. So that's why you can split a hydrogen atom into its constituents, an electron and a proton. But if you try to do the same thing for a proton, it's like you pull something out, try to pull a quark out, but then the force gets stronger and stronger. So something's got to break, basically. So you can't really completely cleanly separate. So in that sense, there's no clean split. But there is another sense that you can have more like a dirty split.
So when you're talking about cleanly split, I just want to make sure I'm on the same page. It's that there's very little interaction between what is being split. But in the case of the strong force, if you're trying to pull something out, it's very strongly interacting with, try to pull out another quark, it's very strongly interacting with the other quarks and gluons. So it's difficult to do a clean split. Is that more of what you're saying?
Yeah, the harder you pull, the harder it pulls back.
Yeah.
And then if you pull too hard, it snaps and creates children.
Yeah. So basically, we recently at my home, I've been trying to make like pizza. So it's like working with the dough. You know, when the dough is not so sticky, you can just remove your hand. It's clean. Everything is clean. It's a clean split. But the dough is so sticky, like the strong force. Your hand is in there. It's all stuck. Everything is stuck together. But if you really try to pull very hard, and you end up with a mess, like just dough everywhere. So the similar situation is happening actually with the proton. And in particle physics, we call this the brown muck. I think there are a few different terms.
Oh, why brown and why? Yeah, just brown muck. What is that about?
Because it's all different colors mixed up.
Yeah, it's a very colorful analogy because it's the strong force, and for reasons that I don't know if we'll go into, the strong force actually has 3 different types of characteristic, and it has nothing to do with color at all. But because we know that there are also 3 different types of primary colors, mainly to do with the cones in our eyes, really. So people kind of make that analogy. They call it the color force. So the brown is referring to the mix of all the colors, I think.
Okay, that makes sense. So now you put us in this sticky situation, pun not intended, in which like it's difficult to remove a quark, but does that mean it's not splittable? Or I mean, I guess our notion of splittable has become a bit more tricky to define. So is it possible to do like a quote unquote dirty split of a proton?
Yeah, I would say that's definitively yes. And a lot of times, if you really try really hard to bombard the proton with something, like that's what you do when you try to split something, right? Just try to smack it really hard, like blast it with something. A lot of times, these dirtiness ends up creating more protons or some other additional particle. So it's not like you break proton into 2 different things. A lot of times you smack a proton, you end up producing maybe even more protons. Maybe you turn some of them into a neutron, and then just stuff comes out. So it's not just like you're splitting. You're just like almost like more like obliterating it, and just this dirty stuff comes out.
I see. Is there a way to explain like very simply how do we know a proton is made up of these like quarks and gluons? Kind of maybe Mikey, if you know the history of that, or like how do we figure that out? Or it's too out of scope question. We can table that.
Okay. Well, no. I mean, there's the textbook answer, which is it came from collision experiments. So it's very similar to the way people discovered that atoms were made up of smaller stuff, but a little bit different. So just to recap, the way people learned that atoms were made up of smaller stuff was they shot basically little marbles at the atom, and they noticed that most of the times it went straight through, which indicated that most of it was empty space. And then like follow-up experiments showed that there's actually these smaller structures in there, and it is actually mostly empty space. So they did similar experiments with protons. It wasn't that they found that there was empty space, but when they knocked protons, what they found was this thing that seemed to be like oscillating, like kind of like essentially like elastic rubber bands. But essentially that indicates that, we can think of the proton as a bunch of little marbles that are held together with rubber bands. And when we knocked it, the oscillation of those rubber bands was exactly the kind of behavior that we observed in the proton.
Yeah, let me just add. I don't know if this is historically accurate. I think it was some of the work done by Beer King and the company. So so basically they try to, like Mikey said, they try to collide protons with other protons or antiprotons with each other at increasingly higher energy. And the interesting bit was that the higher energy the collision was, kind of the more clean the interaction, the stuff that comes out was. Clean in the sense of more like a theoretical sense. But then what the inference was that that means at higher energy, which also means smaller scale. We talked about that before, because due to quantum physics. So that means at more and more energy, at shorter and shorter distance, the interaction is becoming weaker. When it's weaker, it becomes cleaner. So if you extrapolate that, if at high energy the interaction is weak, that means at long distance that the interaction gets strong. So through some of that experiment, they're able to extrapolate certain features of the strong force. That it's, first of all, it's kind of counterintuitive. Like the farther away two particles is bounded by the strong force, the stronger it is. So it's kind of like a rubber band structure. But as you get as the rubber band kind of get less and less stretched out, these actually behave like normal particles, basically, like electrons and, well, I guess electrons and other more fundamental particles.
Huh. And it's up to a certain limit, because I'm not interacting with the strong force like on a day-to-day basis, right? It's just the inside the proton or neutron or things that contain quarks and gluons, right?
Right. Yeah. Yeah. And I also want to follow up on something that Tim said about like the cleanliness, because he mentioned that it's in a theoretical sense, but it's actually, I would argue that it's literally it's clean in the sense when we're talking clean versus dirty before, right? So if I try to pull a quark out of the proton, the harder I pull, the harder it pulls back. Right? Mm-hmm. And if I pull too hard, eventually that rubber band snaps and lots of new particles are created from that energy. But if I pull the particle out fast enough, then it's possible to pull it out so quickly that the rubber band doesn't have time to get tense yet. And so for a very short amount of time, you can have the quark separated from the proton. And that's why people had to smash them so hard to see the structure. You have to actually smash them very, very hard so that the quark pops out so quickly that just for like 1 billionth of a second, it's physically separate from the proton before the brown muck appears.
Huh. One thing I thought with the strong force, that it interacts at the speed of light, because the force carrying particle, the gluons, are massless. So if you separate it out, like, how can it be quicker than speed of light, or how
it's strong at the speed of light though?
Okay.
Yeah, they do interact at the speed of light. Is there an intuitive way to explain that?
Yeah, I guess everything is at the speed of light at that energy. But the more energy you inject, the wavelength of these particles. I mean, keep in mind, ultimately everything is quantum mechanical. You know, particle has sort of like a shape, a wave-like shape. So depending on the shape of these particles, how wiggly the wavelengths are, the interaction will be a little different.
Yeah, and it's exactly. If everything did travel at the speed of light, then quarks would not be confined in protons. So if you can actually send the quark traveling close to the speed of light, then time is frozen because of relativity. So essentially, it can exit the proton before the interaction gets strong, before the.
So I would say that there's a lot of kind of mucky business to do with the quarks and gluons. And mainly because they're so strongly interacting, and it's good that's how you brought this up. Like for a lay person, you can say, well, why do I care? I don't see any quarks and gluons flying by. Like electrons, maybe I can feel it when I eat food. Chemical reaction, that's electron happening. Like, why do I care about the strong force? Like how is it real? But it's precisely because of these attributes, because they're so strongly bound together. like everything that's bound by the strong force, it's completely stuck. So they're completely stuck to each other. So basically, ordinarily, you wouldn't be able to probe the internal structure. But occasionally, when we are able to interact with the internal structures of these quarks and gluons, there are a lot of interesting things and even like technological implications and whatnot. But
yeah, I guess like I also want to now look at like a more like big picture view in which you're trying to probe the structure of like a proton, for instance. So you take two protons and like smash them together at really high energy. Could you walk me through kind of what that process looks like and kind of like as events sort of unfold, like two protons collide and then something happens and some stuff comes out of it? Like, can you describe that a little bit more?
We could give like a schematic view, right? So these two protons are approaching each other in slow motion. I guess the first thing to understand is that like, so the proton, we think of a proton, we can actually count the number of quarks that live inside of the proton. It turns out there are 3 quarks in each proton.
Okay.
But the true answer is it's like 3-ish. Because if you look inside the proton, there's 3 main ones. But because of quantum mechanics, there's always a probability that particles and antiparticles will appear out of nowhere as long as they disappear in a short enough amount of time.
Yeah.
So you can actually measure other particle species inside of the proton, because they're constantly appearing and disappearing. And if you catch it at just the right time, you can even catch an electron inside the proton.
Yeah, and also gluon. Let's not neglect that. There's a lot of gluons.
Yeah, mostly gluons, and these gluons occasionally split into quark-antiquark pairs, and those occasionally split into, So as these, I guess the point that I'm trying to make now that I think about it is that protons are actually made up of everything. Because of quantum mechanics, everything is sort of inside of everything, right? There's electrons inside of protons. In a sense, there's even protons inside of electrons. And when we collide them, we're simply creating enough energy to release these ghostly particles.
Yeah, people
I forgot about that story. That's interesting.
People kind of refer them to like the popcorn. It's kind of like a bag of popcorn, kind of with different flavor. So you just
what?
I mean, in the literature, this quantum chromodynamics, they're these popcorn models, and they kind of visualize, I guess, maybe not literally the proton, but this brown muck. When you accelerate a proton at high energy, there's this high energy density of quarks and gluons. It's like all kinds of stuff coming together. And as you collide, it's almost like you're cooking a bunch of popcorn, and popcorn keeps popping out, and just stuff comes flying out. And usually once you smash these things, because it's a mess, right? It's not really like a clean collision. It's a huge mess, and a lot of times you just get dozens of mesons and protons or neutrons or antiprotons.
I don't like the popcorn. I don't like it's not philosophically accurate, I think.
But it's anyway, a whimsical. It's a nice picture.
Unlike popcorn, what you start with is essentially what you have. It's just like, I guess the same is true with particles. Okay, so I think the most popular models that people actually use to describe, like, do calculations to predict what's going to happen at these colliders, they actually do use the rubber band model. So in that picture, right, in that picture, as the protons get closer, right, when is the momentum imparted? At a certain point, there's a momentum transfer that causes one of the quarks to be ejected. And when that happens, literally a rubber band forms between the quark and all of its friend quarks that lived in the proton with it. And when that string reaches a threshold tension, above a certain tension, it literally snaps into hundreds, 200s of other particles that then recombine into other protons.
Yeah, let's just say that the mathematics for the quantum chromodynamics, the strong force, is a lot more complicated than like electromagnetism, which is what governs chemistry, right? Yeah. So this is sort of like the strong. We're talking about the chemistry equivalent for strong force, which and like Mikey mentioned, there are multiple different models to think about these interactions, and none of them are exact, but they're kind of more of what we call phenomenological model. They just kind of
the string one is philosophically accurate.
Yeah, but still phenomenological. It's just there's some numbers to kind of say, hey, we can parameterize. We can think of these processes as strings, or we can think of these processes as popcorns popping out. And at the end of the day, the goal is to get these models to fit data, basically.
Yeah. Tim, I think you were mentioning this some time back. Is the reason why like nuclear energy is more like you get more out of it than electrical or like chemical burning things is because when you burn things, you're mostly using the electrons and stripping electrons away. When you use more nuclear, you're actually utilizing more of the wrong energy usage.
Yeah, that's a good. Yeah, that's a very nice point that you brought up. So ultimately, at the end of the day, our strong force is important for us because it is responsible for binding different nucleus together. It's important. Like without a strong force, there wouldn't be things like lithium atoms or like carbon. Even there wouldn't be life.
Or atoms.
Oh yeah, I guess that's true. Yeah.
Anything but hydrogen, right?
Well, there wouldn't even be protons, right?
Hydrogen.
Oh yeah.
There would just be quarks flying around, so the world would be kind of dare I say, not so interesting. So indeed, because like all this dirty stuff also brings with it like immense amounts of energy. So that's why fusion, just with way less fuel, if we can achieve it, will burn way more brightly. Like fusion reaction typically operates at, I don't know, like millions of, is it million Kelvin? Or I think it's millions of degrees Celsius.
But so, actually, we shouldn't forget that it didn't happen by accident. It's basic, right? Like when stars explode, they essentially like compact stuff into these like, they compact like, protons into these like 100 proton configurations. Like, the uranium atom is like this. It's only created in supernovas. That's what it takes to get enough energy to create this fuel cell. And it's basically a dense fuel cell full of this strong force energy. And when we find it, we can break it and blow stuff up.
Yeah. So what I'm getting is that intuition is pretty spot on, and that's why we should care about what's inside a proton, because of eventual energy efficiency if fusion does succeed.
Yeah, there's our ability to harvest it is important, but hopefully there's something important beyond that. Although,
and also it's interesting, right? Yeah, it's a very interesting type of force. Like even though on appearance it's very different, it gets stronger as we move further apart. Like if you and I have strong forces, it'll be a huge mess, right? The world will be strongly interacting. But it turns out the mathematical principle governing them it's the same. It's just one number. The interaction strength is different, or of course it's just a few numbers that are different. So that's remarkable. The very different, drastically different physics comes from the same mathematics, and it tells you something about fundamental nature.
I think what it tells us is that you can't really split anything, right? Like even if you split a proton and an electron, even though they're apart physically, they're still entangled until they interact with so many other things, that it becomes like a brown muck.
It's very, very deep. So we're basically on time. Is there anything you guys want to say to conclude? Any last thoughts?
That was my conclusion.
Yeah, I guess. I mean, I suppose we could summarize a bit slightly better. Like, unfortunately, many of our episodes, it's always like the answer is ambiguous. But but when you get to fundamental physics, you know,
Life doesn't have simple answers.
It's true. Yeah, it's not so obvious what we mean by split or not. And of course, we can definitively say that you cannot cleanly split a proton. Like that much is true.
Split anything.
Yeah, but then again, can you ever cleanly split anything? But the answer is that we definitively know that protons can be thought of as made of something more fundamental. So we could split it in a dirty way. We could very much so. So I would give the thumb. I would personally give a thumbs up that we can split a proton.
I would say it.
Just straight up. All right.
Cool. Yeah. So with that, I'd like to thank everybody for joining us, and we'll see you all here next week.
All right. Thank you, guys. Thanks for listening.
Thanks,
see
everybody.
you guys. Bye.
Bye.
All right. Wow, that was pretty